Sorting algorithms. One of the classes of algorithms used most often in real life are sorting algorithms. These arrange certain objects in a line according to a specific property of the object. In our examples, we will most often sort sets of real numbers. In order to simplify the discussion, we will assume that all the real numbers to be sorted are all distinct. But if we allowed multisets of real numbers, the algorithms would still work with minor modifications. BubbleSort. There are n children standing in a line and they are of all different heights. We would like to rearrange the line so that the children are in increasing order of their height. What is the best way to achieve that goal? The question at the end of the last paragraph is very imprecise. What makes it imprecise is the word best. That is, we have not said what we mean by the best way. We will revisit this problem in the next chapter when we will formalize our ways of describing the efficiency of various algorithms. For now, however, let us say that we measure efficiency by the number of pairwise comparisons an algorithm makes. That is, the less pairwise comparisons an algorithm makes, the better it is. So the best algorithm is the one that makes the smallest number of comparisons. One idea that naturally comes to mind is the following. Let A1, A2, A3 until AN denote the heights of the n children, with AI being the height of the child who is currently in the ith place of the line. Let us compare A1 and A2. If A1 is less than A2, then the relative order of the first two children is the desired one, and we do nothing. If A1 is greater than A2, then the relative order of the first two children is not the desired one, and we ask them to change places. Note that in either case, we have made one comparison so far. After making sure that the relative order of the first two children in the original line was the desired one, we compare the heights of the two children who are currently in the second and the third position of the line. If it is the desired one, that is, the second child is shorter than the third, then we do nothing. Otherwise, we ask them to change places. We then continue the same way, that is, we compare the third and the fourth children of the current line, and if they are in the wrong order, we ask them to change places. Then we compare the fourth and the fifth children, and if they are in the wrong order, we ask them to change places, and so on. The first part of the algorithm will end after we compare the two last children of the then current line and made sure they were in the right order. After that is done, we can be sure that the tallest child is indeed in the last place of the line. Indeed, no matter where he was in the line, once our swapping procedure reached him, he moved back on place in each step until he reached the end of the line. Example 17.2. If n is equal to 5 and originally the children's line corresponded to 4, 1, 5, 2, 3, then this first round of comparisons will take place as follows. 1. Start with the 4, 1, 5, 2, 3. 2. As 4 is greater than 1, interchange these two children to get 1, 4, 5, 2, 3. 3. As 4 is less than 5, do nothing. 4. As 5 is greater than 2, interchange these two children to get 1, 4, 2, 5, 3. 5. As 5 is greater than 3, interchange these two children to get 1, 4, 2, 3, 5. 6. End of the first round. Unfortunately, the tallest child is the only one who is surely in his right place after this part of our algorithm. Indeed, it could even happen that the second tallest child is in the first place. The reader is invited to check that this could happen if A1 is the largest of all AI and A2 is the second largest, or if A2 is the largest and A1 is the second largest. The reader is also invited to check that for any positions I and I plus 1, with I which is less than or equals to n minus 2, we cannot know for sure that the child in position I is shorter than the child in position I plus 1. Therefore, we will now repeat almost all the steps of the first part of the algorithm. That is, we compare the first two children of the current line, and if they are in the wrong order, we ask them to change places. Then we compare the second and the third children of the then current line and proceed in an analogous way, and so on. The last pairwise comparison we will make in this round in comparing the m minus 2 minus second and n minus first children of the then current line. Indeed, there is no need to compare the n minus first and the nth children of the line, since we already know that the latter is the tallest of all n children. After this second round of comparisons, we can be sure that the second tallest child is at her right place, since she was taller than anybody who got compared to anyone in this round. Again, nothing more is assured. Therefore, we need to run another round of comparisons on the first n-2 children of the current line again. That will make sure that the third tallest child gets in his right place, and so on. When we run the ith round of comparisons, the ith tallest child will get in his right place. Therefore, when we run the n-1st round of comparisons, the n-1th tallest or second shortest child gets in his right place. At that point, our task is done, since the remaining child is automatically in his right place, namely the first place. Example 17.3. Continuing the process started in example 17.2, we would proceed as follows. 1. Our starting point for the second round would be the line 1, 4, 2, 3, 5. 2. As 1 is less than 4, we would do nothing. 3. As 4 is greater than 2, we would interchange these two children to get 1, 2, 4, 3, 5. 4. As 4 is greater than 3, we would interchange these two children to get 1, 2, 3, 4, 5. 5. This would end the second round of comparisons. In this particular case, no further comparisons would result in any changes, since we have reached the increasing order. How many comparisons will we have to make while rearranging the line of n children? The first round will take n-1 comparisons. The second round will take n-2 comparisons, and so on, with the ith round taking n-I comparisons. Therefore, the total number of comparisons that we will have to make is the summations of n-I, summing with index I starting from 1 to n-1, which is equal to the summations of I summing with index starting from 1 to n-1, which is equals to n choose 2. As we have mentioned before, the procedure of arranging n objects in a line in a previously specified order is called sorting. The sorting algorithm we presented above that used the subsequent comparisons of adjacent elements is called BubbleSort. If we imagine that the objects are arranged vertically, then the largest, second largest, third largest elements will rise to their correct positions as bubbles in water. In a generic programming language often called pseudocode, the BubbleSort algorithm can be described as follows. For I starting from 1 to n-1, do for j starting from 1 to n-I. Do if aj is greater than aj plus 1, then let t equals to the values of aj, then let aj equals to the value of aj plus 1, and then let aj plus 1 equals to the value of t. Here the value I tells in which round of comparison we are, and the variable j tells which comparison of that round we are currently carrying out. The temporary variable t is needed so that while we declare the new aj, to be equal to the old aj plus 1, we do not lose the value of the old aj before we assign it as the new value of aj plus 1. A generic programming language or pseudocode is a loosely defined concept. It describes algorithms in a way programming languages do, but without the formal constraints. It helps to get a quick overview of what the algorithm does.